Our task in this lecture 3 is to describe motion. We're not caring about the causes of the motion yet. We're just going to be describing motion. And we're describing motion in more than just one dimension that we were talking about in the previous lecture. And so what we're going to need to do is use the vector mathematics and the tools we built in chapter 1, lecture 1, and we're going to apply those to what we learned in chapter 2 to describe motion in one dimension. So, for example, we were talking about our vectors represented in some format like this: x I hat plus y j hat plus z k hat. Well, we're going to use vectors like these, but instead of a, we're going to call them, for example, r. So introducing the position vector r. And this x, y, and z, of course, correspond to the components of the vector in the x, y, and z axes of our Cartesian plane. So, of course, to describe motion, we must first be able to describe a particle's position in space. If we don't first know its position, then we can't describe motion from one position to the next. And so if this is our position vector r, let's say we have a particle that is moving from point 1 to point 2. So let's see. So we have a particle moving from point 1, and it moves along this path to point 2. The way that we would calculate its displacement, its change in position, is by calculating delta r. So we have some p1 is given by some vector x1, y1, and z1, and p2 is given by x2, y2, z2. Two different positions described in a three-dimensional xyz coordinate system. And so if we're trying to find the displacement, we would just take r2 minus r1, because that's what that delta symbol means, which would be x2 minus x1 I hat. I'll go down so I don't overlap, plus y2 minus y1 j hat plus z2 minus z1 k hat. And let's say that the particle moved from position 1 to position 2 during some time interval delta t. So we have the particle moving or displacing its position through some time interval t1, t2. So delta t, t2 minus t1. Well, then its average velocity, right, just like before, average velocity would be given by the position vector r2 vector minus position vector r1 divided by t2 minus t1. Time is not a vector, it's a scalar, but the result is still a vector. So we have delta r position vectors divided by delta t. And its instantaneous velocity, using the language we built up in lecture 2, instantaneous velocity v, start a good amount over here, v would be the limit. So delta t goes to 0 of delta r over delta t, which is otherwise known as dr dt. Still a vector. And so, to take it one step further, since now we know that r is a position vector in 3 dimensions, dr dt can be broken up into its component derivatives, right? So dx dt I hat plus dy dt j hat plus dz dt k hat. So if we had values for x, y, and z, we could take the time derivative and find out velocity in each component specifically, and the total velocity vector given an ijk component form. At every point along the particle's path, the instantaneous velocity vector, so if this is our P1, right, position 1, the particle moved along this path to P2, the velocity vector, which I probably should have switched colors to talk about velocity, but points tangent to the path at that point. So velocity vector at this point is tangent to the path. Yeah. At this point, it's tangent to the path, and so on. Right? And the magnitude of velocity, again, same tools that we built from our previous vector lecture. The magnitude of velocity, I'll write it out, magnitude, we express like this with 2 big bars on either side. It's not absolute value, it's magnitude when it's applied to vectors in this way, which would otherwise be written v without its vector, right? So it's the magnitude of the vector v is equal to the square root of vx squared plus vy squared plus vz squared. And it's worth noting that you might not always need all 3 dimensions. It might be unnecessary to count the z direction because all of your motion might be happening in a 2D plane. Actually, the example that I gave here of this particle's path, this only existed in a 2D plane. It might be difficult for you to see if I drew a particle path in a 3-dimensional plane, right? Something like this doesn't show up as much to you, but it's a very curly path in 3 dimensions, so we would need x, y, and z. But for up there, we only need 2. And there's a lot of real-world scenarios that only use 2. So an object that I just threw, a projectile, which we'll talk about next or soon, it exists exclusively in a 3D plane, or a 2D plane. And so you might not need all 3. And magnitude, in that case, would just be the ones that are relevant to you. So vx squared plus Vy squared, say, which is what we'll be doing with projectiles.